Ladies and gentlemen, this is Itai speaking. Today I want to give you guys a brief overview of how the Embraer engine and wing anti-ice system works, as it has some inherent internal logic that is not immediately intuitive to anyone unfamiliar. I will not cover any malfunction handling with this system today, except for some system design logic examples. I will first give an overview of the system and some general considerations we take into account, and then we will jump into normal procedures associated with the system, aka how to use the engine and wing anti-ice system in the Embraer E-Jets E170, E190. For the demonstrations, I'm using Fieldair E175 version 3 on Prepare 3D version 4. This is a mostly good model, but not without its flaws and inaccuracies. If I spot an inaccuracy that doesn't reflect real world operations well as we use them, I will try to point them out, but no promises. That brings me to my next disclaimer, that this video is just for entertainment and enrichment. It's not a substitute for any real-life training. If you're a real Embraer pilot using this video to supplement their training, be my guest. It sometimes helps, but please take it with a grain of salt, and as always, any information you hear from me, you need to take it to your study materials and verify and just cross-check it, and also know where to reference it later on when you need it. Just company-provided official sources, that's the main thing, always. Finally, this video is loosely based on the SOP used in my company, which I cannot share. There can be variations in procedure or even what systems configurations are installed between the operators. So with all of that being said, we are in cold and rainy Chicago O'Hare Airport, about to fly this thing to Newark. So let's get started before I get soaked. The Embraer E170 190's family anti-ice system, or as it's usually called, ice and rain protection system, goes beyond just the engines and the wings. It includes things like heating for flight instruments, smart probes, windshields, water pipes within the aircraft, etc. Today, however, I only want to focus on those components that use the bleed air system to heat the elements. Those items are, of course, the engine and wing anti-ice system. The engine's heating consists of hot air heating the engine cowling ring. You can see that here, the engine cowling ring, that silver part here, to prevent ice from forming there, disrupting airflow and potentially breaking off into the engine itself, causing damage. For the wing anti-ice, each wing leading edge in our aircraft consists of 4 leading edge slats of 1, 2, 3, 4. You can see the partitions between them. The wing anti-ice system heats the outboard 3 slats on each wing. So anything from the engine and towards the towards outside of the airplane. So 2, 3, and 4 on each side are heated, leaving the slat closest inboard of the engine. This one is unheated, so this one will not get anti-ice, unfortunately. I'm sorry. An important detail to note is that the APU-generated bleed air cannot be used for anti-ice purposes. Using bleed air, which is essentially very hot, high-pressured air taken from between the compressor stages of the turbine engine inlet, is very effective in heating up those large metal surfaces of the airframe, but it comes with certain costs. First of all, it has the inherent risk of leaking hot air into unwanted spaces and creating a potential fire hazard. Therefore, this system is monitored for any leaks, but we won't cover that today as it's part of the fire protection system. The second thing, it has significant performance impacts, which are worth noting. On takeoff and climb, as the bleed air is taken from the engine compressor, this air is not used to generate thrust. Therefore, the takeoff and climb performance will take a hit. For takeoff, it means longer required runway, or to put it in terms we actually use, for a given departure runway and present conditions at the airport, like we are right now in Chicago, in certain temperature and wet runway and wind, etc. So that's a given. For that given, we get a lower maximum takeoff weight. It would be harder to meet minimum altitudes and climb gradient requirements, and therefore potentially lowering max takeoff weight even further. So maybe the runway is enough, but right after the end of the runway there's a big crane which requires us higher climb gradient immediately after takeoff. That's called the second segment climb. So maybe we'll take a hit on that as well. Not maybe, we will take a hit. Maybe we can't comply with it anymore. So we'll need to even lower our maximum takeoff weight to make sure that we are out climbing whatever requirement it is. So we need to make sure we're capable and legal to perform the departure procedure. Later on in the climb, using the anti-ice would cause us lower climb angle, which would make it harder to out-climb certain threats. It could be altitude restrictions, ATC requests, could be traffic, or it could be even weather. On descent, the engines will have to be at a certain minimum thrust setting in order to generate the minimum amount of air required to heat up the elements. So if it's idle, it might not be enough air to provide. If the engine is idle, we might not get enough air to provide the required bleed air that we need in order to get sufficient pressure to the anti-ice system. While the engine FADEX will take care of that minimum thrust figure, so we can put the thrust levers to idle, the engine will maintain said minimum thrust, but that minimum thrust would be slightly increased, so it may shallow our descent angle if we're trying to descend using, for example, flight level change mode, or if we're descending on VNAV path or flight path angle or vertical speed. The airplane will meet those path requirements, but it may speed up, and if we're not too careful, it might overspeed or not meet any pre-programmed speed restrictions, for example. So we just need to be aware of those limitations. We can monitor the engine and wing anti-ice system using the MFD, which is multifunction display, MFD anti-ice synoptic page. So from that menu, we'd go all the way down to anti-ice. Each engine takes the bleed air from its compressor. From there, the bleed air can go directly to the same engine's cowl anti-ice valve. So this is the anti-ice valve for this engine. So this is the engine cowling. Okay, that happens before the engine bleed valve for that engine. So that's the engine bleed valve for the engine. You can notice that the bleed is taken from before it. So the bleed valve I'm talking about for engine 2, this is the bleed valve. Okay, right now it's pushed in, so it's the normal position, so it's enabled. I could push it out and it would be disabled. But nevertheless, that entire thing I just mentioned, that happens before that valve. Okay, and therefore engine anti-ice operation is not affected by whether or not this valve is being forced to close, or is malfunctioning, or there's an MEL or something like that. Another interesting note is that the engine cowl anti-ice valve, when failed, is said to be open, as in, if the valve is malfunctioning, we will get the cowl heated. As you can see, wing anti-ice, though, is taken from after the respective bleed air valve. So if that side bleed air valve is forced closed or failed, the air can still flow to that side from the opposite engine bleed air through the crossbleed valve, and that's done automatically when needed. We don't need to do anything. It's the crossbleed valve is operated automatically, provided it's not forced or failed or closed, or something like that. As an example, if bleed 2 valve has some irregularity sensed, it will close. In this case, we can heat up engine 2 cowl because it occurs before that bleed air, and we can use engine 1 bleed air through the crossbleed valve to heat up the 2, 3, and 4, well, the right wing anti-ice. In another example, if we had engine 2 fire, one of the things we would do is we would pull the engine 2 fire handle. One of the things that the engine 2 fire handle does is it forces the bleed 2 valve to close and the crossbleed valve to close, as well as other things. So if we do that, we can clearly see that if the crossbleed valve would be closed and the bleed 2 valve is closed, there would be nothing to heat up the right engine the right wing anti-ice. The right engine would be obviously shut down, but we don't care if it accumulates ice too much at this stage. But the right wing would not get anti-ice. So typically after a fire handle requiring procedure, engine fire, severe damage, stuff like that, we would also see a note: avoid or exit icing conditions. So that's something to note, and that's the reason why, because that fire handle forces the crossbleed off. Even if the crossbleed is on and we're using, so forget that failure, but let's say just the bleed is off. If we're using the only one engine to heat both wings, sometimes we would need to maintain a certain thrust to be able to provide the entire, well, both wings anti-ice from the same engine. It's worth noting that this display is slightly wrong. The APU here seems to be connected to the anti-ice system, which is honestly wrong. The APU cannot provide anti-ice bleed air, so it would just force the bleed air from the APU would force itself closed whenever we're using anti-ice. Another thing we can't see at the moment in this display is whether or not so right now the anti-ice is not operative. We will see that later, but when in flight we would see ice condition note here, and it would also show here as well. And that's happening because the ice detectors that I showed you at the front, when they're detecting ice, we can see the ice condition both here in the ICAS and here if we go specifically to the system's anti-ice synoptic page. The airplane has two ice detectors on the nose section. They're basically small pieces of metal, such as there would be the first thing to accumulate ice if we would accumulate some. You can see it right here. This is the ice detector, not to be confused with the true air temperature probe and the air data probe, the smart air data probe. So those are the smart data probes. This is the true air temperature. These are the ice detectors. So we have one on each side, like so. Okay, and kind of the top whiskers in the nose section, if you will. So they, as they're small pieces of metal, they would be, as I said, the first things to accumulate ice if we were to accumulate some. And as we're flying through icing conditions and ice builds around them, they would vibrate differently. Once they do, they would send different signals electronically, and that's how we would detect ice. And the ICAS display ice condition would set off and trigger the rest of the computer to treat the current as ice condition. If during flight ice condition is detected, so we would see ice condition blue message here, the engine and wing anti-ice valves would be commanded to open and remain open for as long as ice condition persists. After the ice condition does not persist anymore, an extra 2 or 5 minutes after ice is no longer detected, we would still get the anti-ice. So either 2 or 5. Why 2 or 5? There's 2 configurations possible to install. Usually the older one is 5 minutes. The newer system configuration is only 2 minutes. After ice conditioning stopped being detected, and for another 2 minutes the anti-ice has been on, there's still no more ice detected. The wing and anti-ice would be commented off. That was during flight. We need airflow over those ice detectors to keep that to make the ice detectors work. They rely on airflow over them with the precipitation to accumulate the ice. On the ground, either before takeoff or after landing, the ice detectors don't really provide us that indication. Therefore, on the ground, we have two different stages: before takeoff and after landing. We would cover them in just a second in the normal operations section. One thing to note is if at any point the ice conditioning has been detected during flight, the airplane basically says, okay, we did accumulate some ice, so here's anti-ice, Mr. Captain and FO. We would try to get rid of as much ice as we can, but the assumption is we're also accumulating ice in other parts of the airplane that are not heated. For example, the tailplane or the trailing edge of the wing or the upper surfaces. So remember, the surfaces that are actually heated are very, very small compared to the entire airplane, that is. So if at any point during flight ice condition has been detected, the next message we would see, also in blue, is ice protection stall speed, which basically means, hey, from now on, all the reference speeds, which means the green dot and the maneuvering speed, they would be increased to compensate for potential loss of lift from said ice. And usually in that case we would increase our VRF and V approach by either 10 or 11 knots depending on the speeds. So that's worth noting. Is it significant? It might be, because let's say I have a 4-hour flight, and during climb, so let's say we're flying from cold Chicago to the Bahamas. During climb we may have picked up some ice conditions, so we've dealt with it. We had anti-ice on, and we got the stall protection ice speed. That message stall protection ice speed does not reset until after we've landed. So, which means in 4 hours, when we land in the Bahamas, we would need to increase our VRF and V approach by 10 or 11 knots, which is quite significant, and it does increase our landing required runway distance. So we might find ourselves, let's say we're flying to Key West, for example, which has a short runway, and by the way is often very warm. Still, legally, we have the stall protection ice speed. We would have to increase the speed and then try to compensate, maybe by selecting flaps full landing, for sure using auto brakes as much as we can, but it may just make us too heavy for landing in that runway. Then we might consider burning some fuel, but in some cases, when the runway is extremely short, it may just make us not good to land, so we might need to divert because of that. Just a small, interesting operational chain of events, because we pick up like 5 seconds of light rime ice on the climb out of Chicago. So we're now pushed off the gate, and we're about to take off, and we're about to taxi out. Now, I want to discuss first of all, what is icing condition? So I'm separating this from whether or not the ice detector has detected ice. Quick reminder, it's not going to happen on the ground. So what do we call icing condition? Anytime we see visible precipitation or moisture when we're at or below 10 degrees Celsius. And that includes if we're flying through or taxiing through fog less than 1 mile visibility, or rain or snow, something like that. Obviously now it's raining, and the temperature has dropped to about 3 degrees Celsius. So obviously it's kind of cold. The thing is, it's kind of misleading with the 10 degrees. First of all, don't be misled by using the system's status page where you have the TAT and SAT here. They're not operative on the ground because same for the ice sensor, the ice detectors, the TAT probe also needs airflow to be reliable. So would it display values here? I'm not sure. Either way, it's specifically noted not to rely on them on the ground, only in flight. I think specifically above 60 knots, but don't catch me on that. You're willing to comment if you think that's wrong. So we don't rely on those, we just rely on the temperature given by the ATIS or the METAR or whatever that is. And clearly we are at about 3 degrees Celsius, which is right around 35 degrees Fahrenheit, and it's raining. So clearly ice conditions. The fear is that in some areas it would become even colder, and some ice can accumulate, or when we actually build up speed and the pressure around certain points in the airplane reduces. This is with the pressure, the temperature also reduces, and we can still accumulate ice even though the residual temperature might be as high as 10 degrees, or in this case 3 degrees. So how do we set the anti-ice to on as we want it? So first of all, during the pre-flight checks, we verify this is the ice protection panel. So windshield heating, it's on the ice protection. Those don't be confused. Though the engine 1, 2, and the wing anti-ice, when it's pushed, it means that this respective system is deactivated. It's pushed out. It's forced to be deactivated. Okay? So when it's in like that, it is enabled on the automatic mode. So this is the mode selector. It's either auto or on. So in auto mode, this is the logic I'm describing to you. When it's on, it's just on. It turns on anyway. Test we never use. It's for the maintenance personnel. So for example, if the mode would be turned on and I would push out wing, we would basically turn on the engine 1 and 2 anti-ice, but not the wing, because it would be forced out. So back to the original point, during pre-flight checks, we made sure that the mode switch is in auto. And then as it comes down to setting up the performance, we would usually set the performance at the gate. Not always, or sometimes there's a change. Sometimes there's a change in the departure runway, or sometimes just simply the temperature dropped between, say, 11 degrees before we pushed and 5 degrees by the time we maybe had a delay and there's a cold front coming, and now it's cold. So I took the liberty to do the rest of the performance, as in the zero fuel weight and the takeoff performance, etc. So that's all set. From that point, and I hit toga, by the way. From that point, I want to go to the TRS. Let's see if I can get rid of you. The TRS button, which is a thrust rating selection. We do that for every takeoff. In my company, we usually take off with climb 2 unless absolutely needed otherwise. Then we go to takeoff data set menu. ATIX is always on. That's unrelated to this lesson or this video. Ref ECS will be on as well. Okay, and then anti-ice. We can go engine, which would turn the engine anti-ice only, or all. Now, what does it govern? Basically, if we're anticipating icing, as we said, right now, and icing condition is not being detected automatically by the airplane. So, if we're anticipating icing condition anywhere from the gate through taxi and takeoff and until 1,700 feet above field elevation, or 2 minutes after takeoff, if anywhere until that time we're anticipating icing conditions, so below 10 degrees with visible precipitation, we would use ref anti-ice all. Okay, and what it does is exactly what it is. It would turn the entire anti-ice, wing and anti-ice on until 2 minutes after takeoff or 1700, at which point that logic is dropped and the logic of the ice detectors kicks in. And if at that point they detect ice, the anti-ice system will stay on. If it doesn't detect ice, it will simply go off. So I'll just finish setting it up here. Takeoff temperature, it's we said 3 degrees. And the runway is not contaminated, just wet, and we can use flex temperature, let's say to 36 degrees. And it's all obviously would be calculated meticulously, but for that argument's sake, let's say this is what comes out. So right after I did that and hit enter, look now what happened. Now the engine TDS ref anti-ice all, so that's enunciated, and since both engines are already on, okay, oh, I forgot to turn on the APU, so let's do that now. But now we basically have so the APU is shutting down, that's fine. Engine TDS ref anti-ice all, and engine anti-ice engine 1 and 2 valve open. We can see that here. Valve is open. Okay. Now, why is the wing anti-ice not activated yet? I told the airplane, hey, I want the entire anti-ice system to work. Why is it not operating? So the reason is it would not activate while taxiing, and it will automatically activate once we are accelerating past 40 knots during the takeoff roll. So then we would just simply, they would open, and we would see also the wing, anti-ice wing valve open or something like that. So obviously APU would not be part of this equation at all, because as we said, I think that's the third time, APU cannot be used for anti-ice wing and for anti-ice purposes. So in this situation here, so this is right now with the APU out of the equation, this is what we would actually see at this stage. Engine anti-ice being green. Crossbleed, I don't think it would be open, to be honest, so that's probably not realistic. But then the wing anti-ice would activate at 40 knots, reaching either 2 minutes or 1700, which most likely is going to be the 1700 because it's less than, like, about a minute after takeoff. The ice detector takes over. If ice is being detected, they would stay on. If not, they would turn off. If they do, remember what we said, if ice condition exists, we would also see this condition here, and also we would get stall protection ice speed. But as long as we didn't positively detect ice on the airplane, we don't have the stall protection ice speed. Another thing that's worth noting, just so it doesn't surprise you, as we're flying through 10,000 feet, so we're climbing through 10,000 feet, the wing anti-ice goes through an internal built-in test. So we will spontaneously, just through 10,000, we would see the wing anti-ice turns on, and I think after like 30 seconds or so, it turns back off. So it's nothing to be worried about. It's just something that automatically happens by the airplane. So that's before takeoff. Now, after landing, so let's turn off the anti-ice again. Yeah, so now you see the engine anti-ice is closed. We don't see the message anymore. The wing anti-ice is obviously closed. So let's say we've landed. So this is the before takeoff, and we said in flight the ice detectors mandate what's going to happen. Now after landing, it's neither nor, right? It's not the takeoff dataset menu that's governing, nor the ice detectors can give me much information. It's especially prominent when you land in a perfectly nice day in an airport that has some snow on the taxiways, for example. Okay, the snow is contaminated. The snow is contaminating, and by the way, this is an addition to what I stated earlier about what is ice condition during taxi. Also, when the surface that we're taxiing on is contaminated by, is it wet or is it snowy or something like that. So in order to avoid the ice accumulating on the engine, we would want to turn the anti-ice on. So how would we do that? We are not detecting it automatically, nor do we have the takeoff dataset menu. So under normal conditions, really this is the only time we would ever touch the stall protection mode, the ice protection mode, and turn it on. Okay, once it's on, we can see anti-ice mode not auto. Exactly, it's not auto, it's on. And anti-ice 1 and 2 valves are now open. We force them open. Okay, so this is how we treat it after we've landed. Let's say we've just landed here in Chicago. It's 3 degrees, it's raining, so it is definitely icing condition. We would simply, as part of the after landing flow, we would turn the anti-ice mode to on, excuse me. And after we've shut down the engine, or during shutdown, we would simply turn it back to auto. Another thing worth noting, when we're before takeoff like that, if we've selected takeoff dataset menu to off and we've turned on the anti-ice mode to on, it would throw an amber, a yellow ICAS message that says, hey, there's a disagreement here between what you want, which is anti-ice off for takeoff, versus what you actually are forcing me to do, which is anti-ice on. So pay attention. And that's why we do not touch the mode selector before takeoff, but only after landing. If in flight at any point we clearly see that we're accumulating ice and the ice detectors for some reason are not picking up on it, we can use it. We can force it on. Or, if we seriously suspect we're in icing conditions, that the ice detectors are not picking up, or if the ice detectors have malfunctioned. But I said I'm not going to cover this because it has some internal logic, but we can force it on during flight. Just before takeoff, it will trigger a message, and if that message is triggered, we're not to take off, we're to sort things out. So that's pretty much it. So just to summarize, before takeoff dataset menu with the mode in auto. During flight, ice detectors will make the system work, and after landing, if we need anti-ice, we need to force the system to on via the mode selector. Okay, you don't have to worry about the wing anti-ice, like you don't need to get the wing anti-ice like that before you turn it on, because remember, it doesn't do anything. Wing anti-ice would not turn on until we are at least 40 knots in the takeoff roll. Yep, so I think we've covered these. This is, I hope, gave you guys an overview of when do we use the anti-ice. And that's it. Not that complicated, and thanks to the automation, fairly easy to use once you understand the logic. I hope it was helpful. As always, I'm happy to hear any comments you may have. Otherwise, happy flying and stay warm.